Okay, this is Math 2. We're going to do 66 through 69, or at least partial. For the first one, it says, as you have seen, sometimes a graph of two equations never intersect. However, when they do intersect, how many different intersection points can they have? So it's actually a pretty good question. How many intersection points can two lines have? How many intersections can two parabolas have? What about a parabola and a line? So in this problem, you're going to investigate these questions. So sketch a graph that fits each description. Not every graph is possible. Okay, so the first one says a line and a parabola that intersects twice. So it doesn't really have to be a parabola that's going up. It could be a parabola that's going down. But the fact that they do intersect at 2 points anywhere on the parabola is your first clue. So, or I could have a line that goes across like this, or we can have a line that comes down and have a negative slope, anything like that. Or if you have a parabola that's going down instead, you can have a line that's cutting across this way also. So as long as you have two intersection points on your parabola, then you should be good to go. Part B, a line and a parabola that only intersect once. So this is actually a fairly easy sketch. There's another version. Obviously, there's more than one version. You can do a parabola that's facing down with a line that's touching the parabola over here, or your line could be touching the parabola like at this point right here, which means that it's kind of going this way. Well, I probably didn't draw that very well, but it only is supposed to touching it at one point right there. Or you can have a parabola going up and down instead. I'm sorry, not parabola, a line going up and down, kind of like that. Okay, so there you go. A line and a parabola that intersect more than twice. Can you intersect a line? Can a straight line intersect a parabola more than twice? The reality is no, it can't. So anywhere that you're going to put a parabola, let's just say the original going up, if you only have one line, and I'm going to use a paperclip as a line so that you can get a fairly good example of it. If you only have one line, then the reality is no, it will not intersect more than one time. No matter where I put this line, if I go down, if I go up, it's still going to only touch twice. If I move it this way, it's going to touch twice. This way, it's still touching twice, one time. So the reality is you only have one try or two, and that's pretty much it. Two parabolas that intersect twice. Okay, so there's that picture. So one parabola is going up, one parabola is going down. Your intersection points are somewhere over here. Two parabolas that have an infinite number of intersections. This is actually kind of funny because the picture in the answer was kind of funny anyways. Let's say you have a parabola. It's going up. Okay. Well, if you wanted to touch an infinite number of times, if you have another parabola that comes through, hey, look, I can make a parabola with my paperclip. Awesome. You would essentially, okay, so let's see, here's my parabola. Let's see, you have, right now they're touching once, right? Right now they're not touching at all. They're touching one time, they're touching one time, they're touching one time. There's still, well, here maybe they were touching twice, right? But technically, the only time a parabola with another parabola has an infinite number of intersections is when the paperclip parabola is sitting right on top of my red parabola, which makes them literally identical to each other, so you can't really distinguish the two of them. So technically they're kind of the same parabola, right? And then as soon as you move it off, you're back to touching like one time. So they're touching infinite, they're touching one time. Now, if you flip it over, obviously they're touching one time, actually two times here, one time right here, two times, and then two times, and then moves off, and then it's one time, and then no times at all. Alright, two parabolas that never intersect, obviously, just any two parabolas. One needs to go down, one needs to go up though, because the up one, obviously, even if they're not on, even if you can't see that they're touching, somewhere up here they're still actually touching one time, at least one time. And then two parabolas that intersect only once, which means that the vertices are next to each other only one time. So the parabola was maybe down here, and then it moved and touched it one time, and then that's it. That was number 66. All right, next one, 67. Solve the system below, then make a complete graph of it on your paper, on graph paper, and confirm your solution. So we need graph paper for this. First, we need to actually solve it. So we're going to solve it by equal values method first, and then we're going to graph it. So we're going to put the equation y equals x plus 5 equal to the equation x squared plus 5x plus 8. And then we're going to solve this. So we're going to subtract 5 from both sides. So we get x equals x squared plus 5x. And what is this, minus 3? Oh my goodness, plus 3. Minus 5, minus 5. It's early in the morning. Can't be held responsible for my math this early in the morning. So 0 equals x squared minus, oh my gosh, plus 4x plus 3. Okay, so we need to solve this. So we have, do we want to factor? Yeah, factoring sounds like a good idea. So x squared, 3, what is this, 1 and 3. Okay, so 3x and 1x. That gives us 4 in the middle. 1 and 3. Oh, this is going to be really easy. Okay, so we have 0 equals x plus 3 and x plus 1. So that means x is equal to x plus 3 equals 0, x plus 1 equals 0. So x equals negative 3 and x equals negative 1. Okay, so at those 2 points, obviously those are not my x-intercepts of my parabola because I didn't just solve the parabola. We had the line. So that means at these 2 intersection points where the x is negative 3 and x is negative 1 is where I will find the intersection of the line with the parabola. So that means I have to actually plug both of them back into the equation to solve for y. So we have x equals negative 3, so that means y is equal to negative 3 plus 5. So that means y is equal to 2 when x is negative 3. And then in the other one, y is equal to negative 1 plus 5. So y is equal to 4 when x is equal to negative 1. Okay. All right, so let's get this graphed. Okay. So our line is going to go, first I need to draw the x and y intercepts. How far up are we going with plus 8? Okay. Okay, hopefully this works. Yeah, it's sitting somewhere up here. Okay, hopefully this works out. So we need to get this graphed. 1, 2, 3, 4, 5. So slope is 1 over 1. Okay, so our line is going to be, oh boy, I think I need to do this on another graph paper. Actually, forget that. We're going to graph this on the calculator. Okay, we're graphing this on the calculator. Okay, so we have, let's see, clear that. We have x plus 5, and then we have x squared plus 5x plus 8. Okay, we're going to graph these. Okay, so there's a line, and then there's a parabola. Thank goodness. Okay, I was totally in the wrong coordinate, in the wrong grid, I should say. So here's your 2. And I'm going to change the window on this really quickly so we can actually see what's happening up in this side. So we're going to go from 0 Negative, we can hang around with the negative 10. Let's do x max at 5. 1. Let's go to 0. 10 is fine. Let's see what happens. Okay. Nice. Okay. So we've got intersection at x equals negative 3, which is what we did find. 1, 2, negative 3. And y equals 2. So there's that right there. That's that point. Negative 3 and comma 2. And then the other point was at negative 1, comma 4. 2, 3, 4. So there's that point right there. Okay, there's that. There's the graph. Okay, next one, 68. Eliana's training for a race in San Francisco, so she has a new running route that includes running up and down a steep hill. Data from her last training is shown that during which 10-minute interval did Eliana run the fastest, the slowest, and justify your answers. Okay, so justification of your answers is just showing me your work. So you actually need to do a little bit of thinking about this one before you actually start doing it. But if you didn't want to do any thinking, then what you need to do is figure out, well, what's the difference between 0 and 10, what was her mileage increase? Between 10 and 20, what was her mileage increase? And then so on and so forth. So between 0 and 10, she increased by 1.1 miles. Well, as you can see in the next one, between 20 and 30, she really increased 1.5, sorry, I shouldn't do that. 2.5 minus 1.5 is just going to be an increase of 1, basically, or 1.0. And then the next one, 3.7 minus 2.5, is going to be an increase of 1.2. And then the last one, 4.8 minus 3.7, is going to be an increase of 1.1. So based on, I forgot 1.5 minus 1.1. This is a 4.4 increase. Okay, so every 10 minutes that of her timing, she's gone well, except for the first one and the last one, she's actually gone a different distance. So technically, she's gone, what was the fastest rate and what was the slowest? So the fastest rate was an increase between 30 and 40, and she went up 1.2 during that time. So the fastest that she's gone was 1.2 over 10 miles, because technically an increase between 30 and 40 is plus 10. All of these are plus 10. So she's got 1.2 miles over 10 minutes. So that gives us an average 1.2 divided by 10 of 0.12 miles during this time interval. She went 1.2 miles per minute. Okay, that was her fastest time. Okay, and then her slowest time was during the interval between 10 minutes and 20 minutes, but it's still a 10-minute interval because 10 plus 10 is just 20. And then she went 0.4 miles during that interval. So 0.4 divided by 10 means that she really went 0.04 miles per minute during that time interval. Okay. During which turn the greatest distance, the least distance. What was Alana's average rate of speed during the last 10 minutes of her run? Okay, so the last 10 minutes of her run were between 40 and 50. So she went 1.1. So 1.1 over 10. So 1.1 divided by 10 means that she went 0.11 miles per minute during the last 10 minutes of her run. So, yeah, so that's number 68. And then let's do 69. Actually, there's not really much to do with 69. You just have to state the vertex. So for each of the quadratic functions below, state the vertex of the parabola. So the first one did it for you, so you can pretty much figure out what to do from here. The x plus 3 squared minus 10.25. So your vertex is at negative 3.5. And your y-intercept for your vertex is going to be at negative 10.25. Okay, and then the rest B and C should be pretty easy to do from there. Okay, see you guys later.